Okay, I'm not showing you guys the calendar because, frankly, you guys don't need to see it. But here's what's going on as far as notes. If you guys notice, this is weird. Check it out. Can you tell the top? What have I labeled the notes?
Chapter 10 notes.
Chapter 10A notes, except it's section 9.2. I don't understand. Here's the struggle. Since we are Joyce and Gerardo, long story short, our book teaches this next stuff weird. And it's in a way that even talking with a friend that also teaches BC, we're kind of like, wait, what? Why? And it might be good, but I would have to totally reorient how I teach this, and with my broken foot, it's not going to work out. So I'm going to teach it old school style, meaning last year style, with the old book. And as such, here's the struggle. I'm calling this technically our Chapter 10 intro. If you guys want to label it in your books, call it the Chapter 10 intro. I don't even like 10A because we're not doing sections 10.1, 10.2, 10.3 in our book right now. Technically, from last year, what our Chapter 10 is Chapter 9B from last year. So it's kind of like this whole Chapter 9A from last year is totally left out. And I don't want to totally leave it out because I like the way that it introduces things. So, there are notes handouts. Struggle. So Joyce, you're going to be able to get it from me before you start taking notes. Basically, Gerardo and Joyce, it just allows you guys to do examples fast because the examples are all printed out for you. Otherwise, we are taking notes in our composition books. But if I were you, I would go ahead and just put little parentheses around the Chapter 9. The other struggle with us doing from the other book is you guys don't have the other book. However, I do have posted on your homework Chapter 10 intro homework, which is really Chapter 9 homework from last year. Wait a minute, it's a Larson book, which means you can use
CalcChat!
Yes! So, how do you use CalcChat?
It's beautiful.
You type it in there. Is it better than Slated?
Yeah. Because it's always right.
I don't know how to get there.
And it's from the actual
Same
book. But you only get the odds, which is a bummer.
Nope, definitely not. That's the old school book.
Or
Yeah,
you
I
have-
can't type.
Oh, you can't
Sam,
type-
can you go over and can you type in calcchat.com? Perfect.
So wait, Misty, should I in our notes we just put like
So
Chapter
in
10
your notes,
intro
if
and
you-
then like 9.2
Yeah.
with the parentheses?
It's not going to help to
And
do
then-
it so you guys stay on top of
What
it.
about our table content?
Do you put the chapters? Then do Chapter 10 intro and then 9.2.
Oh my God.
I don't know how else
That's
to
fine.
do
No, that's
it.
fine. It's fine. It's just funny.
Sorry. Okay, so coming back. You guys notice calchat.com?
Yeah,
Okay, calchat.com. And if you scroll in the calculus books, not the pre-cal or the applied, go find here it is. It's the black one, Calculus 10th edition. This is the one the kids had last year. This is the one that will have your answers for chapter, and this is what helps you also with your notes because now you know where we are. So Chapter 9, Section 2, this is where we're starting. Cool deal. And it has all the odds.
Yeah.
Worked out. And then there's also a CalcChat tutor that you can,
Yeah, and then I don't know understood that.
oh, there it is, CalcChat assistant that you can try to ask questions in like homework-ish times. Yeah, that's about right.
Yeah,
for
that's
homework-ish.
12 a.m. is awesome. Wow.
Yeah, right? Look at them. And they're even telling you like, oh, it's not on yet, just wait, it's coming. Anyway, there you go.
Almost there.
So calcchat.com is the black book, Calculus 10th edition, and then I am posting in your Google Drive. I have it copied off. I just need to get to the office at some point today and scan it. But in the starred folder for you guys, I'll have it under, you know what I'm going to do? I'm just going to go ahead and make, oh, this is awkward. The homework
Just put it
sheets are where they
outside.
always are. The homework sheets are right underneath. Sorry, back. The Chapter 10 intro is right there, so that's like it always is. But for the other,
Just put it outside. We'll know.
yeah, can I just do a whole new folder and I'll just do Chapter 10 intro, parentheses, Chapter 9.
You can just upload the file, or is it multiple?
It was in a program that wouldn't let me save the entire thing as a PDF, so I'm printing them out and I'm scanning them in the office to make them a
Nice.
PDF.
Okay. So yeah.
I'm cheating the system just a little bit. Actually, quite a
Are
bit.
you gonna make them all one PDF together, or you?
Oh, I could do that. Would you guys be okay if I did that?
Yeah.
So
If you do,
so
just
then-
put it as a file outside.
So I'll just do chapter 9 homework, and then just
Just chapter 9 homework.
that should work. And the pages are in there. Yeah. Okay, that works. So anyway, I'm scanning that in there, kiddos, and then the handouts that we do each day. I think I have electronic copies. I can scan that. Gerardo, I don't know. Group chat me if you need the notes from today. Are we all on the same page of the weirdness that is now happening?
I think so.
Perfect. Let's go to notes. Okay. In your notes, I actually want you to write this down. Have your handout close. I know some of this information is in there, but I have pulled out the most important. I don't know what I was trying to say. Record, live stream. What? You can do that?
Oh.
Interesting. Maybe I wouldn't. No, I want to be able to record the computer too. Never mind.
That's true.
E for effort. Okay. Here we are. Section 9.2, series and convergence. Technically, 9.1 last year was sequences, which was our 9.1. So we've already done 9.1. Literally, they were about the same. But now it's time to go on to series. And this is where the whole ball game changes.
Alright.
You ready for this?
So as soon as mine is drizzled.
So, in the backboard, I'm going to be keeping track of things by section 9 point, even though we're in 10 intro. Does that sound good? Okay. So it's kind of like we have 2 chapter 9s. What was the intro? Sam, can you bring me the top 2 pages on that pile? Yeah, both of those. Thanks, bud. And I did a paperclip once upon a time. And I did a paperclip out of my towel drawer. Thanks, Kim. A series. What's a series? The sum of a sequence. Oh. A series converges if its sequence of partial sums, if its sequence of partial sums converge. Now, here's the struggle. I didn't say if its sequence converges. I said if its sequence of who? Exactly. The series converges if its sequence of partial sums converge. What do I mean by partial sums? What you see right there is the Riemann sum. The sum from n equals 1 to infinity. That kind of sounds like bounds of an integral, right? The sum, that's what sigma denotes or signifies. The sum, that's sigma. From n equals 1, I'm just reading it to you, to infinity of a sub n. This is the entire series, okay? This is the entire infinite series. A1 plus A2 plus A3 plus, is there an n? No. Why is there not an n? Why is it a dot dot dot? Because it goes to infinity and beyond. An infinite series is defined as the limit of a sequence of partial sums. Now, here's partial sums. These are the important guys. Partial sums say, the first partial sum is the first term. Second partial sum is the first term plus the second term. Third partial sum is the first term plus second term plus the third term, etc., to the nth partial sum, the sum of the first n terms. However, an infinite series, it just keeps going. So as you guys look at this box down below, I'm having you literally write this in your notes. Number 1, you need to study it. Number 2, it keeps it nice and neat and organized in our composition book. And number 3, it is that stinking important to realize a series converges if its sequence of partial sums, not terms, partial sums converge. And this is where the biggest new topic of Calculus 2 comes in.
Is there a difference between little n and big N?
Little n is technically talking about the nth term of the sequence, and big N is talking about the nth partial sum. They're just trying to keep them as separate as possible. Does that make sense? plus little n is the number being plugged in, and big N is the upper bound. That's a better way of putting it. Now here's where the struggle comes in, because kiddos, when we were doing sequences, weren't we taking the limit as n goes to infinity of a sub n? Which is still going to be important, but not in the same way as this is. The series converges as long as its sequence of partial sums converge. Why is this a struggle? Well, grab out your calculator.
Wow, I actually brought mine today too.
Yay, go team! I'm just bringing it out. The rest of us don't have it? Alright.
Mine's dead, so
Why is it dead?
I used to use it.
We used to use it.
So they can't use it now.
Doing this in algebra 1 is just clear cut. Okay, go back. Sequence mode. Is that a thing?
Yes. Mode set.
If I were you, I'd still write it down that way you have it. Does anybody have the older calculators with the yellow button, or do we all have newer ones without the yellow button? Okay. Perfect. If you guys have a yellow button, we're in trouble, but if you don't have a yellow button, then we're good. Come on. Sorry, he's right in the way. Can I move him? Go. There it is. Yeah, it's about 4-ish. Sequence mode, the SEQ. N is our little variable button, that's the X. And we have these new options that we have to think through. The nice thing is when we were doing sequences, remember recursive and explicit, weren't we kind of dealing with sequence mode? But what's different is we're not just putting the a sub n formula in, we're putting the entire series in. Which is a bit of a struggle because we're going to have one variable being the index, which is our k, but our n is going to be our upper bound. So things change just a little bit. And once we have that written down, I can go ahead and zoom in on one example that I've done. This is actually on your note packet. It's the first 4 problems. I'm going to zoom in on an example that I've solved. Now this is just exploratory. We're just trying to figure out why on earth, oh that 5 is annoyingly over there. Oh well, I can't fix it. Oh, can I?
How do you know what the lower limit is?
Like, so n equals 1. It starts at 1.
K equals 1.
Or k
Yeah.
equals 1.
Or it could be k equals 0, k equals, not usually k equals 1. It's usually 0 or 1.
Got it, and upper bound
It's
is
just how far
the
you go.
infinity.
It's the n. Yeah.
Or the,
Yeah.
Which is why we're going to make this our variable, because of, then with our graphing calculator we can go 10, 100, etc.
How far along?
Okay, you guys ready? Does this make sense how I inputted the first example? And min, 1. Our u of n. Sigma, where do you find sigma in your calculator? Ah, look at you guys.
oh, I found it 0. Maybe? Yeah.
Okay, I put it in my sequence mode. There we go. We're filling in stuff. We have that. Where'd you find it, Amanda?
It's under math.
Yep.
And then 0.
If you scroll to 0, which is somewhere down here. There he is. Summation. Ta-da!
Can you do it like alpha plus 2?
I'm not sure if it's up there.
Maybe.
Is it? Oh yeah, it is. Number 2. Nice. Okay. Oh, I didn't want to put that much. Okay, so we need to have an extra variable. We can go ahead and just use k. That works. I guess maybe you could use x. No, because the x button is the n. That's annoying. So then our alpha, I'm just using k to keep it like our expression. Oh, sorry, Amanda. Which number is k?
What is K? The little parentheses, the left.
Oh, thanks. Okay. So k equals 1, got it. And then our upper variable is n, that's our actual variable button. And then we're plugging in our actual sequence, which is negative 1 over 2. You could use the alpha, but whatever. All raised to the k. Remember, not the n, but the k. And then we got it. KK. Just don't say it again. What's the u of n min? You're welcome.
Okay.
What's U of? Wait, U of is the actual thingamabob, right? And U of n is standing for, in case you guys don't see it, U of n is standing for our partial sums. Because it has a sigma, right? Okay. So U of n min means, hey, what's the partial sum of 1? Wait, what? Oh, what's the first term? Okay, well, plug in 1. Negative 1/2 to the first is, you see why I'm just plugging in negative 0.5? Got it. Now, why am I going to my table? What am I?
So we can just plug in random numbers.
do?
And
Oh, because I need to approach infinity. And how do I approach infinity in my calculator? I plug in bigger and bigger numbers, yeah? Now, something that you need to see, if you go to your second graph, I did second, right? Table, yeah. Do you remember what your table setup needs to be there in order for you to type in numbers?
independent.
Ask, good. It needs to be under ask for second window.
I see.
See it?
Independent and ask.
Because you're going to be plugging in your own x values. You don't want them to do it for you.
Maybe Bob.
There we go. And then you can always get rid of whatever is in there previously by hitting delete, delete. Now, how quick is it to plug in 1? Oh, no big deal. How about 2? Oh, no big deal. How about, oh, that's taking forever, 10? How about 50? Uh-oh. Uh-oh.
You broke it.
Uh-oh. What is your calculator literally doing right now?
Adding it all up.
Plugging in 1 and 2 and 3 and 4 all the way up to 50 and then adding them all up. So, can your calculator maybe show you stuff?
Yeah.
Yes. But are you going to be able to go to infinity very easily? No. So this is merely just an exploratory device, or if you are allowed to use your calculator, you can at least have something, some way of working with this infinite series in your calculator. Does that make sense? Okay. So from all of this work, what can we probably assume? Now, that's dangerous. We're not proving it. We're just assuming that this infinite series converges to.
Negative 1.
Yeah, and why did I say converges? Because, oh my goodness, doesn't it look like it's converging? However, question, what are the terms of the sequence? What are the terms of the sequence converging to? If we were to ignore the series for just a second and go do old-fashioned stuff from our section 9.1, what would be the limit as n goes to infinity of a sub n? Negative 1/2 to the infinity.
1, right? Isn't that, because it would be negative 1 and 1?
This is fluctuating between 1/2. Oh no, it's not. Never mind. 0.
Because it's not growing as you raise it to higher and higher powers.
It's going straight.
Oh, true.
It's shrinking. Now it is oscillating between negative and positive, but it's not going towards two fixed points that are, that would be DNE, but instead we can say it's approaching 0. Now, does this limit equal the same thing as this limit?
No.
Why not?
Because one's 0 and the other one's negative 1/3.
Okay, that's true, but why are they different? Isn't it the
Partial
exact same
sums.
thing?
No.
Partial sums.
No, because this is the limit of who?
Of a sub n.
Of the sequence only. And what is this the limit of?
Partial sum of the series.
Of the entire series. Does that make sense? Okay, number 2. You guys don't have to plug it in. You can go ahead and check out my work. I plug in 1/k. Get it all set up in my graphing calculator. Check out my table. 1, 2, 10, 50, 100. It took it a long time to do the 100. What's going on?
Maybe 1 is 0.
Well, wait a minute. What goes to 0? The sequence or the series? You see it? We have to reorient our brains in that the limit as n goes to infinity of a sub n for this one is 0 also. Bottom wins, right? But what's going on with this infinite series?
Adding.
You might think it might be getting closer to something, and so you might make your calculator work for a long time to go to 1,000. But the long story short is it just keeps growing. It just keeps growing.
At 1.1 can number be negligible? No?
You would think.
Yeah.
But it's not. This one is one of the most common divergent series that you might think would be convergent. It's actually called a simple harmonic series. Has a spiffy name, we'll talk about it later. Number 3. Long story short, once you go to your table, he would end up being, for our purposes right now, let me just say he is going to be convergent. And number 4, you guys should be able to look at him.
Divergent.
Divergent. Why?
Fluctuator oscillating.
He's oscillating between 1 and -1, 1 and -1, 1 and -1. I'm going to leave it to you guys to go ahead and play in your calculator because you guys don't know how to have your calculators. And figure out what is number 3 converging to. I told you he's converging because I know all these tests that we still need to learn over the next few weeks, literally. So I was able to say that. However, my question is, what is he converging to? Use your calculator to figure it out. All right, let's keep going. There are some series that are very special. And then there are some tests that are very special. We are technically just embarking on a Calculus 2 topic called the convergence, divergence, tests for infinite series. This is just the beginning. As I said a little bit earlier, this is going to take us quite a while to get through. And as you guys were doing some of your practice AP stuff, you saw stuff about convergence, divergence, etc., right? So we're just starting on this big picture of convergence and divergence tests. In section 9.2, we have 2 tests, the easiest 2 tests, the fastest 2 tests. But the problem is we need about 9 tests. These are only 2. Sometimes they apply, sometimes they don't. Sometimes they apply, sometimes they don't. So, out of the 9 different convergence and divergence tests, here is test number 1 and test number 2. Test number 1 is the geometric series. This is endeavor number, struggle. I do not know. 12? I'm not sure if I've updated them. What did we have last section? We had L'Hopital's, no, that was from the Forevers. We didn't do the faster or slower, right? What was section 9.4? Improper integrals, did we make that an endeavor? Oh, I was on that day. Struggle. That was on the video, that's why it's not coming up. Right now we're just going to leave it a blank, because I need to figure out the improper integrals. I think I might want an endeavor for that. Yeah.
I'm pretty sure there was one that we had that was 10, because I remember having to look it up for that.
Yeah.
But then if you want to do the improper integrals, that might be 12 or 11.
Okay, 12. So theoretically this is 12?
12 is
We'll just keep it as a blank box. Geometric series. Hey, wait a minute. Geometric, we talked about that. What's geometric?
Common ratio.
Common ratio, yeah. Except this isn't a sequence, and this is a series. So it's the sum of a geometric sequence, right? But what do you notice? The sum from 1 to infinity of a times r to the k equals a sub 1 all over 1 minus r if r is in between -1 and 1. Now this might seem silly unless you talked about sequences and series in pre-cal. And you remember in pre-cal there was a formula for the n partial sum of a geometric series. An old pre-cal formula.
I don't remember, but I remember not like
An old pre-cal formula for the geometric series was S sub n is equal to a sub 1 times 1 minus r to the n all over 1 minus r.
like you said something about convergence.
We talked about convergence and divergence way back then, getting ready for today. That's exciting. Looking at that formula up above, why does it converge to a constant only if r is in between 1 and -1, not including 1, not including -1.
It won't be 0 on the top or 0.
This is the nth partial sum, once again from geometry. This is the nth partial sum formula. So we could take the limit as n approaches infinity, not of the sequence, but of the partial sum. And on the left-hand side, that denotes the infinite series. But on the right-hand side, well, how do you take the limit to infinity? Oh, what's the only place that n occurs? In the top, r to the n. Okay, well, give me an example of a common ratio. 2. If you raise 2 to the infinite power, who wins? The top. Oh, that's not a constant. If you raise -2, that's still going to keep on getting more and more and more negative, positive, negative, positive. It's oscillating and growing. That's bad. But what if you plug in 1/2 to the nth power? What's that going to approach? 2. So then 0, well, a sub 1 times 1 minus 0 is a sub 1 over 1 minus r. Oh my goodness, isn't that the exact same thing this formula says? And it's been quite pixelated. But anyway, the only time this limit is going to exist, this will only equal an actual L if r is any of the numbers between -1 and 1.
Should we know that formula?
You don't need to know the nth partial sum, but if you did know that one, it might help you remember this. But otherwise, no, memorize this one right here.
Oh, shit.
The infinite sum is equal to a sub 1. A sub 1 meaning the first term. The first term over 1 minus r if r is in between -1 and 1. Geometric series converges if r is within those values and diverges otherwise. This is one of the few convergence and divergence tests that allows us to say converges if this and diverges otherwise. But this will only work if I have what type of series?
Geometric.
Yeah, if it's not geometric, this test doesn't apply. So, long story short, eventually there's going to be a test on, well, there's going to be a quest on 9.1 to 9.3, which are half of the tests, and then 9.1 to 9.6, which are all of the tests, the convergence and divergence tests. You're going to be given a series, and you have to look at it and go through a checklist of, number 1, is it geometric? Because if it's geometric, it has its own test. If it's not, oh, I'll struggle. Cross that one off the list. Let's go try something else. So, real quick review of geometric, even though we just did it. Common ratio, right? Times r, times r, times r. Why is there a green line? I have no idea.
When you were zooming out, I think it like.
Oh, is that what it was? Thanks, kid. Let me go see if you get rid of it. Oh, it does work. Go team. Remember common ratio? Nth partial sum. Oh, we just talked about this. Oops. Nth partial sum is a sub 1 times 1 minus r to the n, all over 1 minus r, but yay, it's not in the yellow box. Infinite sum is k equals 1 to infinity of a times, which could be seen as a sub 1, r to the k, equals the limit as n goes to infinity of s of n. We already talked about when it only works. Sorry, did the notes, but I did it at the top of the page. Okay, so geometric series. Ready? You guys have your notepad, anything?
Yes.
Examples. We're going to basically go until the bell rings on examples.
All of them.
Question. Find the common ratio. Determine if the series converges or diverges. Then compute the sum of the series.
Times 1.
First of all, looking at it, is there a common ratio?
Yeah.
What is the common ratio? Which means that we can say we are using the geometric series test. Yes, and I'm kidding. Copy exactly what I do, except you can print instead of do cursive. Geometric series, why? We're working towards that test where we have 9 different possible approaches and we have to choose one that works. This one, we would use the geometric series test. Why? Because it is a geometric series, and how would you prove it to me? Tell me the common ratio. what can you say as a result according to the endeavor card because r equals 1/2?
That it converges.
Mm-hmm.
Sounds good.
My iPad has its sound turned on. Sam, can you turn the sound off on my iPad? Turn the sound off. Should be on the side.
A is 1, right? Our A will be 1?
Yeah.
So you have to.
What would that be? Yeah. Whoa, whoa, whoa. Why am I putting so many words?
Just like for an upper key.
We're proving it.
You have to say since
Yep.
R is.
Yep.
Okay. Let's see that.
Why am I doing that? Because I'm making you memorize the test. Ooh, go team.
Did you have to put R since R or just?
You can just put r equals 1/2. You can just go ahead and have the rest there. Does that make sense? Dun 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 dun. You're gonna get used to me writing these little snippets of, first of all, what test are we using? Second of all, what fact points us to what we're about to state as our conclusion? Number 2. What do we got? Is it a geometric series?
Yeah, maybe 1/3.
Good. So we can say, yay, we can use the geometric series again. Why? Well, because r equals -1/3. So what can we say as a result? Just a shortcut, I won't write the summation every time. But we can say, yes, this converges to, what's a sub 1?
1.
Over 1 minus -1/3, right?
1.
Because it's a sub 1 over 1 minus r, and r is a negative. So then we're going to have 1 over 4/3, which is going to end up equaling -1/3 is in between -1 and done. Dun 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 dun. Alright kiddos, technically you can start homework, but we still need to see a whole nother test, so no stress. No stress. Let's say let's not start homework, but you guys finish 3 through, how many do we have? Yep, finish 3 through 6, that's it. And then play around with the calculator so that you can have it as a resource as we learn more tests to explore sequences with. Nope. Series with. Okay. Now we're on sequences. Nope. Series, not sequences. Struggle. It'll be an adventure.
Christy,